Yeah, so I spent a substantial fraction of my time in Singapore. So this is actually this is pretty close for me. So I'm going to be looking forward to programs at this institute. So in the last year, I got really excited about the intersection of topology and photovoltaics. So I'd like to share some of my excitement. Yeah, so a brief outline. So first I'll review the shift component of the photovoltaic current. I'll tell you how the shift vector is related to the intraband and the interband Berry connection. So this is the shift vector that appeared in yesterday's talk, but now reappearing in a photovoltaic effect. So then I'll tell you about my result, which is the first known class of wide bandgap topological insulators with a large shift current. I view it as a baby step towards a topological solar cell. Just a remark on previous works. Previous works have studied the shift current in topological semimetals or topological insulators with a small band gap. So therefore, the shift current is only large at low frequencies. But if you really want to exploit, the fact that the solar spectrum is peaked between 2 to 3 eV, you really need a wide band gap topological insulator with a large shift current. So I'll briefly review the phenomenological theory of the direct photocurrent by Kraut and Baltz. So first I'll present what the current looks like in an inhomogeneous medium. We can separate the current into 3 terms. There's a drift term, a diffusion term. These two you can combine into a so-called generalized Ohm's law, which you might be familiar with if you studied. If you studied the doped silicon solar cell, but there's an extra contribution, which is a second order in the electric field or linear in the intensity. We can express this other term as a product of a nonlinear conductivity times EB and EC. ABC are Cartesian indices, and just because the electric field is odd under inversion, spatial inversion, and the current is also odd under spatial inversion, so this conductivity is zero unless the medium breaks the central symmetry. Right. So my goal is to maximize this second order DC photocurrent in a homogeneous noncentric crystal. So the fact that it's non-central symmetric, it comes from the intrinsic crystalline structure. But even this second order current has 2 contributions, a shift and a ballistic contribution. So the shift current it originates from the shift or the displacement of a quasi-particle wave packet as it transits between Bloch states. So I'll label Bloch states by their band index M and N and their momentum K and K prime. So when you have optical excitation, there's a corresponding shift. When you have relaxation due to phonons or impurities, there's also an associated shift. So each of these jumps results in a displacement of the wave packet. There's a second contribution, which is the current due to the ballistic motion of quasi-particles, and this is only possible if the quasi-particle distribution f of k is not equal to f at minus k. Okay. Oh, I should add that this is even though the initial excitation could preserve the fact that f of k is even in k, it is the subsequent scattering in a non-central symmetric medium that results in this f of k not equaling f of minus k. So one difference between the shift current and the ballistic current is that the shift current can be non-zero even if f of k equals f of minus k. Okay, so I'm going to, my more modest goal is to actually maximize the shift component of the bulk photovoltaic current for a homogeneous noncentric crystal. This shift current can be expressed in the following form. So this sum over all possible block-to-block transitions. This shift vector has a dimension of position. So this is the displacement of the wave packet I was telling you about, and there's this is multiplied with the forward transition rate minus the backward transition rate. So I'm going to focus mostly on the light-induced shift in the limit where the light wavelength is long compared to the atomic spacings. So I'm going to neglect the photon momentum, and therefore this light-induced shifts correspond to vertical transitions. So the shift vector now only depends on a single value of k, but it depends possibly on two band indices. And in the next few slides, I'll explain why this shift vector depends on the intra and interband Berry connection of the electronic wave function. First, the intraband component. Right, so I think a useful analogy in this context is to go back to Heisenberg's one of the most revolutionary insights in quantum theory, this notion of the quantum leap by Heisenberg, where he realized that if you excite a hydrogen atom, you cannot think of this excitation. You cannot imagine it with some intermediate trajectory. It's literally if you want a teleportation between one Bohr orbit to another Bohr orbit. So really the shift current is a solid state analog of Heisenberg's quantum leap, right? So now you have an excitation between a valence and conduction band, but now the shift or the quantum leap is really between localized 1A orbitals. But how do we translate this intuition into some formula? So we know that we can always Fourier transform a block state to a 1A orbital, and when we do so, the position operator is in one-to-one correspondence with I gradient of k, and therefore, we have this relation that the expectation value of the 1A orbital equals the Berry phase, or the integral of the intraband Berry connection, defined in this way. So this is immediately suggestive that that the shift vector is just a difference in the two intraband Berry connections, where say M is the Berry connection of the band before excitation, N is the band after excitation. Okay. But this can't be the complete story, because as a matter of principle, the shift vector, it should depend in some way on the polarization of the light. So there's a missing interband Berry component of the shift vector, right? And so here, to motivate it, I'll go to I'll tell you a bit about the wave packet interpretation of the shift vector developed by Brillouin and Sturman. So that you can construct, say, a wave packet in a band N by linearly combining block states, and when you calculate the expectation value of this wave packet, the expectation of the position, you get some terms like the intraband Berry connection. This is the usual group velocity term, and then there's this term which is the gradient of the phase of this this complex wave function in the block basis. Okay, So if we apply, just ordinary time-dependent perturbation theory, we know that the wave function in the conduction band is proportional to the polarization-dependent dipole matrix element. But by the way, so what I do in this talk is if you see a dot above an equality, it means I'd likely have dropped some factors of 2 pi or some fundamental constants just to emphasize the quantities that I think are important. Okay. So this the off-diagonal matrix elements of the position operator is just equal to the the interband Berry connection, where C stands for conduction and V for valence. Is defined here. Okay. Okay, so this is then the complete expression for the shift vector. There's this intraband component, the interband component. Separately, they're not gauge invariant, but when you combine them, they are gauge invariant. The same formula, but okay, so staring at this formula, you might then imagine that because topological materials have a large interband Berry phase, it's suggestive that the shift current is large for topological materials. And this has been many people have thought that and they have worked on it, but despite all that work, lasting several years now, no topological invariant has ever been found to be associated to the shift current. And I believe there's a fundamental reason for that. And the reason is that really, for all those topological materials that were studied previously, it's always possible to tune the Hamiltonian to be central symmetric while remaining in the same topological phase. So that is to say, you're able to tune the Hamiltonian to the point where your shift current is 0. Right? This implies that the topology of the wave function is not a sufficient condition for a non-trivial shift. So you really need to impose supplemental conditions, and typically these conditions are imposed on the energy dispersion. For example, in this work, the condition is to impose a small band gap for Z2Ti, and in some of these works, the condition is to impose a tilting of the direct cone or a warping of the dispersion, and so on. Okay, my goal is to really forego all these supplemental conditions. I just want to find a class of TIs for which wave function topology by itself, is a sufficient condition for non-trivial shift. So this class of TIs, if you've been following my argument, they have to satisfy this property, that the fact that they are the property being that being topologically non-trivial is only possible in a non-centric space group. So this property I call intrinsically non-centric. But by the way, this rules out all the maybe more well-known topological insulators that exist in the laboratories, the Chern insulators, the Kane-Milli, the various types of topological crystalline insulators. So I'm going to tell you about 2 propositions for intrinsically non-centric topological insulators. The first proposition is that there exists an invariant that inputs the electronic wave function and outputs an integer. Now, if this integer is non-zero, then it is impossible to continuously tune the shift vector to 0 for all k in the Brown zone. So I call this the shift obstruction. And you see that this formal statement is just a formalization of this more heuristic statement here. Okay, the same statement but more elaborate. Second proposition, that there exists wide bandgap TIs with a large transient shift current under broadband radiation. Okay, so I'm gonna I'm going to spend the next few slides dissecting the sentence. First, I have to tell you, what's the difference between a steady versus a transient shift current. So this is, as you recall, the formula for the shift current. If you consider a shift current in a steady state, these transition rates, they really have to be determined by a kinetic model, where the quasi-particle distribution in the conduction band is dependent on the radiation lifetime, the lifetime of photon scattering for impurity scattering, and so on, right? And so this determines this quasi-particle distribution, which is actually then an input to calculating these transition rates. And it should be remarked that only the steady current matters to solar cell applications, right? On the other hand, there's also the transient photocurrent, which is the early time photocurrent, time, say, less than any relaxation time in your system. And the essential assumption is that you approximate the diagonal component of your density matrix as a density matrix at zero temperature and at zero light, with zero light. And then the off-diagonal elements of your density matrix are then calculated by some Kubo-type perturbation theory, okay? And this transient current is possibly measurable in some ultra-fast experiment with a sub-picosecond resolution. Okay, having explained what transient means, I need to tell you what I mean by a large transient current. I need some figure of merit. Okay, with a monochromatic radiation, we can consider this nonlinear conductivity that's derived in some Kubo-type formula, and it depends on the frequency of the light. Now, for broadband radiation, my figure of merit would be to integrate this conductivity over all frequencies, over the frequency corresponding to the bandwidth, essentially. Okay. And the nice thing about this is that for three-dimensional insulators, this integral is just as units of E cubed over H squared, so it's all fundamental constants. So I'm going to define whatever coefficient F there as my dimensionless figure of merit. So what are the typical values? If you consider prototypical ferroelectric like barium titanate, F is about 0.01. There's a calculation by Tan and Rapp. If you look at the peak in the frequency of this conductivity of, say, a related ferroelectric lead titanate, it's about 0.05 milliampere per volt squared. So this is my result for intrinsically noncentric TIs. Admittedly, these are all model Hamiltonians, but anyway, I think this is promising. So F, this figure of merit, is approximately 10 times the topological multiplier. The frequency average of sigma is approximately 0.1 times the same topological multiplier. Okay. Okay, so this is, in some sense, I've set up the rest of the talk. This is the outline for the rest of the talk. These are the two propositions, the shift obstruction, wide band gaps with large transient shift current. So these two propositions will be exemplified by a minimal model that's reflection symmetric, is in two-dimensional. It's also a two-band Hamiltonian, but you can think of it also as a 3D model if you think about stacking. Okay. But then going beyond this model, I'm going to spend a few words on generalizations of intrinsically noncentric TIs for photovoltaic applications. I think at this point if anybody has a question, I'm happy to entertain it. Sorry, I can't hear you, but the mic is coming.
So what does it mean to deform a system into an inversion symmetric system?
Yes, it's a thought experiment, but the fact that the thought experiment, the fact that you can do it as a thought experiment, it makes you realize that there's really no direct link. You know, okay. So suppose you consider, a non-central symmetric Z2 Kane-Milli type topological insulator. But we know that the Kane-Milli invariant is compatible with inversion symmetry, right? So you can remain in the same Kane-Milli topological phase, but you can, and while maintaining the gap, you can in principle tune your Hamiltonian to something that's central symmetric. But if you can do that, it means that your if you want, you have this phase that is central symmetric, phase that is not central symmetric, but both phases are in the same topological phase. You know, that means that you could be close. Nothing prevents you from having actually a zero or arbitrarily small shift current, because when you are close to the point where you have when you nearly have central symmetry, your shift current is then nearly zero. So nothing prevents you from that situation. So by insisting on topology that is intrinsically non-centric, we can rule out this scenario.
So in systems without central symmetry and well, there could be a large shift current then.
It could be, but then it would not be related. It would not have a topological explanation.
Oh, okay, I see. Thanks.
I think there's one more question there.
So I guess I have a related question or a similar question. So I thought the shift current is a geometrical effect and not topological necessarily. So I'm probably confused about the motivation, because I thought you can have topologically trivial crystal that does have shift current too, right?
Yes, you can.
So,
but the aim here is to have a very large shift current.
oh, and you think that will the topologically protected type of crystals that you need a central like what you're saying,
yes,
is going to help.
Yes.
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 Okay. Thank you.
Okay. Probably I'll postpone the other questions to the end. Okay, let's discuss this shift obstruction. It's worth repeating. So the claim is that there exists a invariant that inputs wave function, outputs integer. If integer is non-zero, then it's impossible to tune the shift vector to zero for all k. And this invariant has a intraband. It can be expressed as the sum of two invariants themselves. One is related to the intraband barrier connection, and one is related to the interband barrier connection. I'll explain first the intraband component. Okay, just to motivate it, you can ask the following question. You know, what type of intraband barrier invariant maximally breaks central symmetry? I'm going to put quotation marks on maximally, but hopefully become clearer what I mean. So if you consider the barrier curvature field strength, it transforms as a pseudo vector under spatial transformations. So if I denote central symmetry as P, then the barrier curvature relates it constrains the barrier curvature at K equal to the Berry coefficient minus k, this is a result of the central symmetry. So then you might say, you might argue that if I want to maximally break central symmetry, I just want to change the sign from plus to minus, okay? That's my argument. Incidentally, this is also compatible with time reversal symmetry. Both P and T invert k to minus k, but of course the fundamental distinction is that one of them is unitary and the other is anti-unitary. So what we want is that the integral of the Berry curvature be large and quantized in half the Brown zone, okay? So I'm going to offer a flat band model that realizes this, okay? So the model is actually quite simple to state. I can tell it to you in like 2 lines. So it's a 2-band model, so you can always express it as a dot product of a 3 vector with the 3 vector of Pauli matrices. Actually, but the 3 vector, I'm going to parameterize it by spherical coordinates, theta and phi being theta being the polar angle and phi being the azimuthal angle. Right. So here's what we're going to do. We're going to replace theta and phi by kx and ky respectively. This is then a model with 3 independent hoppings as an intra-orbital hopping. So blue and red, they correspond to the 2 different orbitals in this model. So there's an intra-orbital hopping, there's another intra-orbital hopping with a different orbital, and then there's this diagonal inter-orbital hopping. Okay? And then by construction, the norm of the vector is 1, so then this is a flat band model. I can phrase it in the sense that the gap over the width is infinite, so in some sense this is as large a band gap as you can wish for. But let me draw your attention to the fact that the polar angle is defined from 0 to pi, but kx is defined from 0 to 2 pi. Okay? So what this implies is that we know that the d vector covers the sphere when the spherical angles are varied. But then, if you then replace theta with kx, it means that the d vector covers the sphere once over half the Brown zone, say with positive kx, and it covers it again in the other half with negative kx, but actually it covers it again with the opposite orientation. Okay. So there's one sort of useful way to represent this information. You can think about the Berry phase that depends on kx, and this is a Berry phase obtained from, say, parallel transport. If you parallel transport a block state at fixed kx over a loop in your Brown zone, this defines this phase that depends on kx. And if you plot it, you see that in half the Brown zone, as in kx going from 0 to pi, the Berry phase advances by 2 pi, and then in the subsequent half, the Berry phase returns to its original value. Okay, I like to call this the reverting Thales pump because, I mean, in an analogy with the original Thales pump, right? So in the original Thales pump, you have to break time reversal symmetry, and then you have this winding over the full period of your Brown zone. But here, you have this advance. You advance by 2 pi over half a period, and then you revert back to the original value. Hence reverting Thales pump. And this reverting Thales pump is compatible with time reversal symmetry. Okay, so I'm going to define a invariant for this pump, which is simply the Berry phase at pi minus the Berry phase at 0 over 2 pi. And I'm going to claim to you that it's quantized due to mirror symmetry. I'm going to give a very rough argument. There's actually, you can generalize this argument so that it's not so rough, but okay. Let's just take the rough argument for now. So if you focus on kx equals 0, let's assume that the conduction band wave function belongs in one mirror representation, and the valence band wave function belongs in the other mirror representation. So then in the Bloch sphere representation, the wave function for the conduction band, say, is always fixed to the north pole, and the wave function for the valence band is always fixed to the south pole, right? And this is so. But the point being that it's fixed, independent of ky, right? So, which means to say you can always choose the wave function to be independent of ky, which means that you can always choose a gauge such that the intraband Barry connection vanishes, which implies the Barry phase equals 0. But then we know the Barry phase is defined modulo 2 pi. So what it really means is that the Barry phase is 2 pi times an integer. And by the same argument, you can conclude that the Barry phase at pi equals 2 pi times an integer. Okay, so that was the intraband component of the obstruction invariant. Let's go on now to the interband Barry component. Okay, let me define a field, a vector field, which is the gradient of the phase of essentially the E dot A. I remind you, E is the light polarization vector, and A with a subscript CV is the interband Barry connection. And we want this vector field to be topologically non-trivial, and also maximally breaks central symmetry, whatever that means. It'll be clarified. So if we, okay, to be topologically non-trivial, that's simple. What we can do is we can introduce a 0 in the interband Barry connection, and around this 0, the phase will wind. Hence, if you integrate the field, you always around a loop, you always get 2 pi times an integer. So let me call this an optical vortex. So the effect of central symmetry is that the interband Barry connection at k equals the interband Barry connection at minus k. So if you think about this purple arrow is meant to represent one of the arrows in this vector field. So this constraint implies that if the phase advances this way between k1 to k2, then parity symmetry tells you that it advances in the opposite way between minus k1 to minus k2. Right. So once again, the way then to maximally break central symmetry is to just flip the arrow. Right. We want to flip the arrow, and the one way we can do that is to change this constraint with a complex conjugation. And this is another type of constraint that is compatible with time reversal symmetry, and for the same reason that time reversal symmetry is anti-unitary. All right, so what this implies is that, parity symmetry, they always relates pairs of vortices with the same chirality, if you wish, but time reversal symmetry relates pairs of vortices with opposite vorticity. So, one implication is that if you find any vortex in a time reversal invariant system, it must break central symmetry. So I'm going to define a vorticity invariant that counts the number of vortices in half the Brown zone. Okay. So I define it by integrating this vector field around the boundary of my half Brown zone, which defined for positive kx. Okay. So to recap, we have defined what is RTP, what is VOR. So I've given you this definition, so you know that inputs wave function and outputs an integer. But the next is to show that this invariant is actually related to the shift vector. To do that, let me define a dimensionless shift by integrating the shift vector over lines of constant kx. Okay. Now, you see when you notice this tilde here. So this is what happens when you convert Keynote to PowerPoint. The tilde becomes much smaller. This really should be a much bigger tilde. But okay, it's just so pay attention. So when you see this tilde, it's dimensionless, okay, because it has been integrated. Okay. To say it's dimensionless, we mean that when it equals 1, this means that the average of the shift vector over the momentum line equals 1 lattice period, say A. Okay. And the claim is that the difference in the dimensionless shift at pi over A and 0 is simply the obstruction invariant. Before I prove this simple thing, let's consider an implication. If the obstruction is non-zero, this equality tells you then there's then a quantized difference in the shift vector, which means that it's really impossible to tune the shift vector to 0 everywhere in your Brillouin zone. Right? So this is proposition 1, the shift obstruction. Okay, but let's prove this claim. We're going to, so the difference in the dimensional shift is essentially the integral of the shift vector around the around the boundary of your half Brillouin zone. And here I've just input our formula for the shift vector. And we see that the first term is essentially if you want, by Stokes' theorem, is the integral of the curvature over half the Brillouin zone. So that is the RTP invariant for the conduction band. The second term gives you the RTP invariant for the valence band. And this third term is just the definition of the vorticity, right? But we also know that the barrier curvature of the conduction and the valence band, they are related by minus sign. Right. And so then RTP of the conduction band is equals minus RTP of the valence band. So hence this equality. Okay, so that proves the claim, but here's a further observation that will also be useful. Actually, each of these dimensionless shifts is quantized to an integer. Okay, so don't forget there's a tilde here. So the dimensional shift at kx equals 0 is simply the Bravais phase at 0. And the Bravais phase, I told you in the previous slide, is always quantized to 2 pi times an integer. And then there's this addition, which, as you can see, can only be also 2 pi times an integer. So this is, well, and then you divide by 2 pi, so then it's always an integer. Okay. And similarly, the dimensionless shift at kx equals pi is always an integer. So that's going to be useful later. So I just want to, I guess, give a proof of principle that the different phases that are labeled by these two invariants are actually realizable in models. So we're going to deform the flat band Hamiltonian model that I showed you a few slides ago. We're going to add 2 hoppings. They're both interorbital hoppings. They're parameterized by alpha and beta. And you see here that this is the phase diagram. When alpha and beta are above 0, this is the flat band limit. But you can see that you can essentially get anything just with these 2 hoppings. Okay. I'd like to now demonstrate proposition 2. That this model actually, first it has a wide band gap, and also it has a large transient shift current with this figure of merit that is proportional to this topological multiplier. But what is the reason for this multiplier? Okay. So I'm going to offer an argument. Let me consider the average of the two-dimensional shifts. Okay. Notice tilde, 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 I'm taking half, so there's the average, and since each dimensional shift is integer quantized, this is then an integer over 2. Okay, so the figure of merit that I defined, just let me remind you, is the frequency integral of the nonlinear conductivity. But that's essentially the Brown zone average of the shift vector. And so then what we get is that this is by an order of magnitude argument is given by 2 pi essentially times the average dimensional shift. Hence pi times this topological multiplier. So that's the argument. This is the numerical substantiation. So this, with the same deformation parameters, the average dimensional shift is -half in this rectangle here, and 0 in the 3 triangles here. And this is a color plot of the figure of merit. Okay, and you see that dark blue is about -12 and yellow is 0. Okay, so it's consistent. But a few remarks about this phase diagram. If I look at the top right corner, so this phase has a trivial intraband Bravais phase. It's also trivial under every known classification. So Robert talked yesterday about several classification schemes. He didn't say all of them, but in all of them, they're all trivial. Okay, but anyway, it's topologically non-trivial when you think about the interband Bravais connection. Okay, and really the large shift is solely due to the optical vorticity related to the interband Bravais connection. If you look at the other corner, this is what happens is that the intra and interband Bravais effects, they cancel out. So the shift is essentially small or nearly 0. So I hope these 2 examples have convinced you. I hope they've convinced you that really you need a complete geometrical theory that treats the interband and intraband Bravais connection on equal footing. Okay, so previous geometrical theories, they are either incomplete in the sense that they neglect optical vorticity, or they are non-topological in the sense that they found nothing quantized. Okay. So I'll say a few words about generalizations of intrinsically noncentric TIs for photovoltaics. First of all, reflection symmetry is not needed. You can do it with rotation symmetry. Okay, so this is this RTP invariant that I defined for you can exist in rotation symmetric systems. Second, you can, 2-band sounds like a pain. You can always enlarge it to n bands with n arbitrary. However, there is a condition on the symmetry representations of both the conduction and the valence band. I emphasize both. Okay, so this is a hallmark of a symmetry-protected, delicate topology. It's not stable topology. It's not fragile topology. And really, the difference results in some qualitatively distinct one-year orbitals and qualitatively distinct surface states. There are other intrinsically noncentric topological invariants, for example, the Hopf invariant, which turns out also to be delicate. And in fact, all known delicate topological invariants are also intrinsically noncentric. I don't know if this is a coincidence or is there some deep reason behind it. Okay, so this is just a series of punchlines. So I've presented a complete topological theory of the shift current, which treats the intra and interband barrier connection on equal footing. And I've introduced this notion of intrinsically noncentric topology, and only for these types of topological insulators can wave function topology by itself imply a non-trivial shift. And as a matter of principle, I've shown you that wide bandgap topological insulators exist with a large transient shift current. As a remark, there are only a handful of intrinsically noncentric TIs that I know. And I conjecture that there are probably many more waiting to be discovered, especially those that are delicate. Also, I happen to think this is one of the few intersections between a fundamental topological theory and I guess promising technological / photovoltaic applications. Yeah, thank you.
Yeah, one or two questions, please. Oh, yeah.
Thank you for your presentation. I have two short questions. First, when you draw a phase diagram with adding two hopping terms, does the band still remain flat, or is there a bandwidth?
There is a bandwidth, yes.
But it's small, so you can still think of it as the system as having a large band gap?
Oh, no, actually at some points in the phase diagram, the gap actually closes.
Oh, I see.
Right. So what, when I gave you when I told you that the figure of merit is 10 multiplied by an integer, I chose points on the phase diagram where the gap is large.
Oh, I see.
Yes.
And also, I kind of missed why the shift current is 10 times the topological number.
Oh, okay. So the argument that I gave actually gave pi times the multiplier, but it's an order of magnitude argument. And in fact, when I looked at models, I find 10 times the multiplier. Sometimes I find 40 times the multiplier. It's an order of magnitude argument that I think works. But I find that the models turn out to be even better. Oh.
Okay. Thank you.
Yeah, one urgent final.
So in the beginning of the talk, why is it important to take homogeneous crystal?
It's okay. So the thing is, with silicon, if you don't dope it, this direct photocurrent vanishes. But that's because silicon is central symmetric. Okay. Now, you can think of it in a few ways. Like, first, can we imagine a homogeneous crystal with a shift current, or with say a photovoltaic current that can compete with silicon? Maybe that's possible. Or you can think of it differently. Can we begin with a homogeneous crystal, which is non-central symmetric and therefore has this large shift current, and can we then dope it in a way analogous to silicon, and then even produce a larger photovoltaic current that might compete with silicon? So I guess that you can view it in two ways.
Okay. Thank you. Yeah.
Okay, now, yeah. Let's end. Yeah, thank you very much. Yeah. Okay.